permissions, but we're ready to begin the workshop with Matt Forrest. And he's a geospatial professional focused on education and scaling technology. I first came across him while I was trying to upgrade my own skills and happened across his really dynamic tutorials on his YouTube channel. So he's the director of customer engineering and product-led growth at Wherobots. Founder of the geospatial teaching community, Modern GIS, and a founding editorial board member of the Cloud-Native Geospatial Forum. He's a Badger and holds a BA in Geography and Sociology from the University of Wisconsin-Madison. So I will be quiet and hand it off to you.
All right, thank you. And apologies about that, the technical glitches there. But I'm excited to be here. And obviously, glad to be talking to a lot of folks in the Big Ten. I have my Wisconsin geography shirt on, which is a little bit smaller than when I got it. But you know, that's it takes time there. But I'm here to talk about cloud-native geospatial and specifically how you can leverage that in GIS workflows. Now, what is cloud-native geospatial, and what does that mean for you? The key reason why cloud-native geospatial was created was there is so much geospatial data, both in raster and vector formats, but primarily this started with raster data, that it was so hard to download and access that data in the traditional methods, meaning that if you need to go collect data from a specific, time or region or anything like that, you usually had to download gigabytes of data. And within that, you might only need a small spatial extent of that data or a small temporal extent, but you were effectively throwing away 60, 70, 80% of the data that you downloaded. So that's kind of the issue that existed. And AWS, Amazon Web Services, kind of had this problem when they decided to host Landsat data. So they hosted it for free. They figured we'll put it out there and people can use it. But the problem was they were just downloading so much data over the web that it made it very difficult. People couldn't get access to what they needed. They didn't want to download gigabytes of data when they only needed a small tile of the actual data. And traditional limits like APIs or things like that weren't really the right way to access this data. So this created a new opportunity to actually make the files themselves smarter and allow people to access data more efficiently. So what did AWS do? And this is kind of where the origin story of cloud-native geospatial begins. The structure is in the files, right? The structure, there's spatial organization, there's temporal organization, the bands for raster data are organized. All of this is made very accessible within the file itself so that you, as the requester of that data, can slice that request and only get the data that you want over the web, right? This is all meant to really serve you as the user or the person accessing that data. The burden for data providers is to move data to these formats and make it very easy to interact with them. And that's what I hope to show you today is how you can actually do that. What's nice about this is that this, just because the name cloud is in there doesn't mean you have to use cloud infrastructure, right? It's much more that the data is hosted on the cloud and there's efficient ways to request that data over the web and actually access it from there. So it's really about making you as the user and able to get access to more data and do that more efficiently. Now, it's also not just for big data, right? This is another, I think, misnomer sometimes within this space. It's that you can actually get data that's updated on a regular basis. You can read in data very efficiently, keep it up to date, and then also be able to slice that temporally to get the data that you need, both backwards or from the current view. There's also very efficient, structure for organizing vector data, specifically complex geometries within the GeoParquet file format, which I'll talk about a little bit here. You can actually structure the data to include bounding boxes and row groups to allow you to do aggregates and slicing the data more efficiently. And then you can actually put these scenes directly into desktop tools like ArcGIS Pro or QGIS and pull them in much more efficiently. So it's basically faster access, lower cost, and you get scalability. You access global temporal data, but you only have to grab the bits that you need. So here's the formats. They're really not that different from formats that we've used in the past, but I just want to explain what's happening within them. So a cloud-optimized GeoTIFF has an internal tiling pyramid, right? A cloud-optimized GeoTIFF, let's say it's 30-meter resolution. It has that resolution across the entire file. Cloud-optimized GeoTIFFs actually have a larger file footprint because it has these pyramids that go up called overviews. And at different levels, it will basically spatially aggregate those to provide better and faster visualization, which I'll show you in a minute here in QGIS. That tiling pyramid allows you to more quickly access and visualize the data, so the requests are much faster. So if you only need to pull at a higher resolution, you can grab that higher resolution and use it there. It also has the tiling within these raw tiles here that are basically, you can choose to set them up, but usually that's in 512 by 512 pixels. So if you only need that one tile, you can pull that much more efficiently. So this is great for imagery, elevation, land cover, these types of data sets. STAC, or a Spatio-Temporal Asset Catalog, is basically a cataloging system to understand and access that. So it gives you a catalog to look through the data, search it, do filtering, and there's even things like actually filtering scenes by the percentage of cloud cover or the actual sensor type of that the data is actually being collected with. So you can actually filter by these different parameters with STAC. GeoParquet is really built for vector data. Now, Parquet is a file format that's been used in the analytics community for a long time. What's unique about it is that it groups data in columns rather than rows. So what helps with that is that if you only need 3 columns, when you're requesting that data over the web, it will only pull those 3 columns. It will ignore everything else that's in there. So think about this: if you have census data that sometimes I've worked with geodatabases that have, thousands of potential columns or records in the data, you only need to request 3. You only have to get those 3, which is a really efficient, especially when you're reading data over the web. What also is within that is these row groups. So it groups the rows by different chunks. These could be controlled by the person creating the file. But let's say that you have a group of, in this case, 4 rows here. And maybe this is a metric of temperature, elevation, it could be whatever. Within that row group, what Parquet does is it stores, row group metadata. So it actually says, oh, I know what the average is for this column. So if you are creating an average over that column, it can just skip over all 4 rows and say, I don't need to calculate this. I already know it. It's embedded within the file itself. So first of all, the file formats are much smaller, right? Compared to a GeoJSON, shapefile, GeoPackage, anything like that. The file sizes are much more, compressed. But then you have all of these efficiencies when you're doing, analysis, aggregations, all these different pieces. Pertaining to geospatial, you have file metadata that gives you the projection, all this other information that we care about as a geographers and GIS practitioners. So it gives you all of those pieces as well. I'll just turn that off here. And then it also has this bounding box over the row group. So it says, let's say you're collecting data and you care about a specific area. If it can look at that row group and say that nothing in that row group touches the bounding box I care about, it can just completely skip over that. Now, we're talking about 4 points in this example, but you could imagine this could be for 100,000 rows or points or things like that. Very efficient to read over the data, skip what you don't need, and just pull in the data that you care about. The final format are these like multi-dimensional array formats, generally grouped in terms of what we call ZAR. And what that means is that it's for like NetCDF, climate data, HDF5. I think I'm saying that right. I always forget the order of those letters. But this is data that you might see from, some of the different climate agencies that are reporting data. It allows you to compress those data over the cloud for faster reads, and allows you to read that for different, Earth measurements for, things like temperature, rainfall, pollution, all these different pieces. So these data formats are pretty widely used, especially on the climatology side of the world, but they are now efficient to read over the web, and ZAR makes all of that possible. Now, there's a few other formats here that, are available from Cloud-Native, but those are the key ones to know. And in the short, why this matters for you is that you can analyze, gigabytes, terabytes, even up to petabytes of scale with just a few lines of code. Or now, increasingly, there's more tools to do this actually in your desktop GIS tools. So if there's global data you want to get access to, you can simply pull what you need and ignore the rest, which is really nice. You can use familiar tools. Esri is adding more adoption for these different formats. The key here is that you query, you don't download, right? You're passing a query off to the files themselves. It will pull what you need in. You don't need cloud infrastructure to do this. I keep kind of, iterating that. And that's kind of like a misnomer in the name. It's like, oh, cloud native, I have to have cloud tools. That's certainly not true. We'll show you one example of that from my work at Wherobots, but we'll show you how to do that in QGIS as well. And then really build for the future. This allows you to build scalable, flexible workflows that evolve with your needs. All right. So for the workshop piece, I have QGIS open here, and I can kind of show you some different tools to interact with cloud native data from this perspective. So this is the University of Minnesota campus. I grew up in Minneapolis, coincidentally enough, so I'm quite familiar with this area. Now, let's say that I want to pull these building footprints into my desktop GIS. So the one way, there's a few different ways you could do that. You could actually go out and try and download all this data yourself. But as we've seen, there's more call for need for this data to be collected from these cloud native formats. There's a plugin here which you can actually collect. And if you go to manage and install plugins, you can download those. And it's going to be called the GeoParquet downloader, which you can see here. So this is the plugin that you need. It allows you to download those from different cloud services. Some of those are like Overture Maps Foundation, which is increasing in data usage and data popularity, Source Cooperative, and a few others. And there's a project to continually push more of this data into cloud native formats. One data set that I pulled in is the data set from Oak Ridge National Labs. So they have an amazing data set of building footprints that are used for things like FEMA. Let me see if we can find the actual, here's the DOI listing. So there's this whole, process that they did to pull all of these different buildings in, label, categorize them, and they're actually used for, efforts, in natural disasters, FEMA, things like that. So they have this really rich data set. It's all in geo packages, I believe. So it's kind of like a lot of data to download and manually loop over and things like that. But what I can do now is actually go here and you can see there's a few different options to actually pull this data in. This is the US structures from Oak Ridge National Labs that I created. And all I have to do is hit OK. It's going to read the spatial extent of the map and then pull that in as a Parquet file. So I can go ahead and download that. It's going to load the extension. Underneath all of this, it's just querying the data for you. It's writing the spatial SQL query to read that data from AWS S3. So you don't have to write the query yourself. And then it's going to download that data in GeoParquet format. So you'll actually have access to that. So once that's downloaded, I have a sample of it here that you can pull in. You can actually, there's another part of the plugin that allows you to read that data in. So we'll go here, and this is a earlier one that I pulled in. You can open this GeoParquet file. Oh, we can actually just pull the new one. So that allows me to set the projection, and I can just hit open, and it's going to do that with DuckDB. And now I have these building files as a layer directly from this. This is pulling from a layer of every building in the United States. And there's really rich metadata here about these buildings. So there's a lot that you can actually do with this and interact with this data. So this is one easy way to do this. You can certainly write the SQL yourself if you want to query that and do that. Source Cooperative is a great place to actually get access to that. So if you go to source.coop, there's a ton of data sets here, both in raster and vector format. This is the data set that we just looked at. Let's see. Here we go, structures. So what you can see what's actually happening under the hood here, you can create an account and get credentials to AWS temporarily to get access to this. But the data is all here. And if you can see that it's just loaded into GeoParquet format, and then it's partitioned into these smaller groups. So it's actually split up so you can query across the partitions, but actually if you just want to download this, what's nice is I don't actually have to do any of that. I don't have to download all of these, 8 or 9 files here that are each about 2 gigabytes compressed. I can actually just write the query and retrieve that in. So that's the power of this, is that it under the hood, what it did, it called out to that, wrote the query, and just pulled that little chunk of data I need from this much larger data set. So that's an example one. For raster data, let's go here and take a look at this. So this is an example STAC browser to actually, if you remember, STAC is the cataloging service that allows me to read this data. If you go to radiantearth.github.io/STAC browser, if you just search or Google STAC browser, STAC, you should be able to find it. This is a collection provided by Element 84 of a lot of different data sets. So if I go here, let's just go forward here. So they have a complete listing of all the data sets that are available here. So let's take a look at the Sentinel-2 data here just to see what's there. And then this allows me to filter across this global data set, showing a sample of like the first things that show up, which are all in Greenland here. But what's nice is I can actually do a spatial filtering. So if I wanted to do a spatial filter, and then this time we'll jump down to Madison down here. And now if I hit this submit here, it's going to pull a spatial filter. On top of that, I can add a temporal extent saying maybe I just care about data in the last, couple months. Now I can submit that and it will just pull those listings here. And then there's additional filters here if you query this by API to get rid of high cloud cover images and things like that. So you can keep looking and eventually we get a clear image here. Now this is part of a complete cloud optimized GeoTIFF that's much larger, but you can see it's just allowed me to filter to this one single tile that I care about here. And if you go in here, you can see that this is just that one tile. And then all of the bands are available here. Now you can do and request this data over the web with Python and other tools if you just care about one specific band. If you want to use it just to download here, you can do the same thing. So if I just wanted the true color image, I can see that I can get access to the S3 URL here and download that as well. Actually, here's the true color image here, and then I can download that. And then now I have that much smaller file here, which is only 300 megabytes to get access to that one raster that I care about. And then I have that. But as you can see, it splits up all of the bands from Sentinel, but it has Landsat, all of these different ones. So increasingly, as you add more data here, it allows you to do that quite efficiently. So what does this look like when you add in processing power and things like that? I work for Wherobots, so if you want to follow along, I know we're tight on time due to the technical glitch, but you can sign up for an account at wherobots.com to get started. There's a free community tier that allows you to create a notebook. All you're doing is creating a notebook that allows you to write Apache Sedona code. So if you're not familiar with Apache Sedona, that is an open source project, Apache Software Foundation project that provides spatial support on distributed computing services like Apache Spark and things like that. So the community tier has a ton of great tools within it. You can actually access a lot of data in the spatial catalog. So we provide a ton of open data from Foursquare Places, Overture Maps, and a few others as well. And then you can actually create and open some notebooks here. So let me back out of here. Once you create your account, you'll get access to these example notebooks. And in here, there's some getting started notebooks to actually help you out. So this will walk you through some of the different things that you can do. Effectively, you create a connection to your compute service. And I'll just zoom in really quickly so you can see that. And then this allows me to read a GeoParquet file into my data frame. So this is a file of New York buildings. I'll load that in. Let me just get this up and running as we go here. And then I can actually interact with this just as I would with Python. You can turn this into a GeoPandas data frame. With raster data, you can move that into Rasterio. So you can write your code alongside of this that you would normally work with, but you can also, kind of use existing code that you have and just pass off the computationally complex parts into something like Apache Sedona. So that allows you can also load in raster data. This is a 1 foot DEM from the New York City. It's a New York City public data set that has a very granular DEM. What I'm doing here is basically, it's not a cloud optimized GeoTIFF, but I can actually create a reference to those tiles here and create tiles on the fly that allow me to effectively use that and query that data. So this allows me to do operations like this in Spatial SQL. If I wanted to get a measurement at a specific point, what is the elevation at this? This is actually the elevation of Strawberry Fields in Central Park, where I live now. I don't live there, but I live in New York. But you can actually get the elevation of that using some simple things here. You can do things like zonal stats. You can visualize data within the context of a notebook, and then you can actually analyze different buildings. So what's great about this is I can get the average using the zonal stats feature of that complete raster and do that for all the buildings in New York that are above the elevation of 0. So that's the operations that you can use here. You can do that, then see the map out from this. So there's a ton of notebooks to kind of get started with this. They all kind of walk you through the different steps that you can go through. But that's pretty much the pieces here. This compute will get spun up here in a second, and then we can run through the notebook. But the key here is that what differentiates the cloud native data is that all this data is living on storage in AWS. It can be in Google Cloud, it could be literally anywhere, and it allows me to do very efficient reads of just the data I care about at runtime. So when I'm querying this data and pulling this in, it's only loading that when that query time happens. So another interesting piece about this is that when I create a reference to data that's living somewhere else, this is not in my system, this is living on AWS in the cloud, it's only going to materialize the pixels that I need. So as I run through this here, as I explained it, I just created a data frame reference to my elevation data for this TIFF. I'm going to create it as a temporary view. And now to get the measurement of this specific point, I can do that here and query that, and it should tell me the elevation at this lat long, which is where Strawberry Fields is, which is 90 feet above sea level. So I can actually, just to show the data here, you can do some visualization. I have a pre-built config file for the visualization, so it'll load in, and you can see the things like the buildings and stuff like that. So all this data is just, what's cool about this is this could be of a much larger file. You can see all the data here with these buildings. That's that Oak Ridge National Labs data set that I showed before. So you can see here, it's all classified and categorized by different things like, land use, commercial, education, residential, so on and so forth. And then here's the kind of the zonal stats function that you can use. So I can create my view for buildings. I'm going to just check my SRID, the spatial reference here, and then I can load in my query here, which will then retrieve the elevation for every building within a certain distance of that building. And then this will actually run and process that query. It's only going to load in the pixels that I care about from that much larger TIFF, which is even more efficient operation. So I'm leaving the data where it is, materializing at query time and running that. And we're adding a lot of other things here to actually add applications like this for things like machine learning and adding in raster inference, object classification, all these different pieces we can add in and distribute over computing very efficiently without moving any data around. So once this runs, we'll load in the map here just to see the results of the buildings with elevation. And then that should be just about it for today. And if I did this right, I think we're pretty close to time, even given the slow start. So yeah, I'll pause there as this map loads.